Water current and electrical current are similar in that they both measure the rate at which something flows. For water flowing through a hose, we typically use units of gallons per minute. For electrical current, we use coulombs per minute, or amperes, to measure current. But now we ask the question of why does water flow through a hose, or why is there electrical current in a wire? Taking a look at the water current first, it is the pressure difference between two ends of the hose that causes the water to flow through it. At a typical water faucet outside of your house, the water pressure is between 40 pounds per square inch and 60 pounds per square inch. In the atmosphere, the pressure is close to 15 pounds per square inch. Water will flow from high pressure to low pressure, and the larger the difference, the faster it will flow. Electrical current works the same way. We know that electrical current is defined to be the opposite direction of the flow of electrons. Now, instead of pressure difference causing electrons to flow, there is another reason why the electrons move from one side of the wire to the other. We learned long ago that opposite charges attract, and like charges repel. This is the source of our electrical current. If we put a large positive charge at one end of the wire and a large negative charge at the other end of the wire, the electrons are attracted to the positive charge and repelled by the negative charge. If we can change where the positive and negative charges are located, we can see that the electron flow changes direction as well. If we increase the number of positive and negative charges at either end of the wire, the rate at which the electrons move is increased, because there is now a stronger force pulling each electron in the wire toward the larger positive charge and pushing them away from the larger negative charge. A common place where we have this large source of positive charges and large source of negative charges is a battery. To create these reservoirs of positive and negative charges, there is a chemical reaction that takes place inside of the battery which allows us to move a negative charge to one side, leaving the other side with an equally large number of positive charges. Now, one side of the battery is very negative and the other side is positive. If we wanted to remove one more positive charge through the membrane, it would take a lot of energy, since all of the positive charges are repelling it. The amount of energy required to move this charge between 2 points is called voltage. We can calculate a value for voltage by determining the amount of energy it takes to move this positive charge from its current location, we'll call that position A, to another location, we'll call that position B. Make a note that in the definition of voltage, it is always measured between 2 points. As an example, a AA battery has a typical value of 1.5 volts. The positive end is 1.5 volts higher than the negative end. That means that to move positive charge from the negative end of the battery to the positive end of the battery, it takes 1.5 joules of energy per coulomb of charge. If we connect this battery to a wire, we can see that the electrons flow from the negative side to the positive side because of the voltage difference between the two ends of the battery. This means that electrical current will always flow from a place of higher voltage to a place with lower voltage. This is just like the water current, which will always flow from a place with higher pressure to a place with lower pressure.